I want to introduce today a new type of function. So you have now in your toolkit linear functions to model things that increase proportionally, quadratic functions to model things that increase and then decrease, so maybe the height of a rocket or something like that. But you don't have anything, right, that can model a phenomena that does not fit any of those patterns. So say something that increases and then decreases and increases and decreases, and the relationship changes over time, right? Well, polynomial functions can do that for us. And these are related to quadratic functions. In fact, a quadratic is a special type of polynomial function, but a polynomial function is anything made up of powers of x here. So here's my example t of x here. In this case, this models the temperature throughout the year in Chicago. So we know that does not follow this pattern, we would die, or this pattern. It's a little more complicated than that, right? So here's the graph. This is obviously sort of an ugly function. It's got all these decimals in there. Here's the graph of that function. 0 degrees, so degrees is the y-axis, of course. 0 degrees is freezing, so it's 32 Fahrenheit. This is in Celsius. 32 is like cold, but not too cold. You're from Chicago, right? We want to know how many times it shows up in the graph of the function. And based on the graph that I gave you, we know this is, what did I call this? T of x? Yeah, t of x equals 0, right? So our zeros are still the same of these polynomials. Notice, though, this has a lot more than the 2 we're used to seeing, okay? 4 times. And you should be pleasantly surprised by that, right? So 4 times relates to x to the 4th. So that is not a coincidence. The zeros of a polynomial function, they have as many zeros as their degree, their highest exponent. Okay? So degree is a new vocabulary term that's good to know. It just means the highest power of x. So this is a 4th degree, or this has degree 4, right? So these functions have as many zeros as their degree. That means our functions with x squared as their highest term have 2 zeros. We already knew that, right? And this has 4 zeros. If I had x to the 88th, it would have 88 zeros. So that's the relationship there. And notice the higher the exponent, the more times the function has to turn, right? So this changes direction 3 times to make 4 zeros. As this number gets higher, the function changes directions 4 times. So that allows us to model more complicated things. Okay? So because we have a complicated function here, it's hard to find these zeros, right? So this is not at all factorable. But what we can do is we can use our calculator to find these. So I'm going to show you a way to do that. It's going to use that calc menu that we've used before. So what I've done is I've typed the function into the grapher, and you can't see the whole thing. Make sure you type it accurately. You should be doing this along with me to help you remember, by the way. And then I'm going to go to the graph, and you're going to get something like this. And it makes sense that we can't see the whole graph, because the default window on your calculator only goes up to 10, right? This function goes up to 12 because there's 12 months. So I'm going to zoom out just a little bit so I can see the whole thing. So go zoom and then zoom out. And then as it redraws, it will look a little bit more like what's given to us. Still cuts off the top, but that's okay because we're just interested in the zeros, right? Now, what I can do to find a 0 is go second, calc, and 0, believe it or not. And then it'll do this left bound, right bound thing. Remember, this is telling your calculator where to look. We've done this before. So left bound, I'm going to go to the left of that 0 I'm interested in. Remember, I asked you for the second time. So I'm going to go to the left of that second one, hit enter, right bound, go to the right of that one and hit enter, and then hit enter one more time. And this gives me 2.5 and some change. So I'm going to round, we'll do 3 decimal places. X equals 2.50 here. And that's about March, right? Because it said January was 0. That means February would be 1, March would be 2, and then it's 2 in a little bit. So middle of March is our 0. That makes sense. It's like in the 30s by the middle of March usually, right? So that is a method to tackle these, especially when they're these more complex real-world models with decimals in them. So super useful, saves you a lot of work. I'm going to write the steps, and then we'll talk about the main idea. Okay, so here's finding zeros on your calculator. These are the steps we just did. Try to make sure you can reproduce this result before we move on. That would be good for you to know. The last thing I'll note is that if you wanted to find all 4, you could do that 4 times, and it would give you all 4, as long as you move the bounds each time. Okay, our main idea is essentially what I wrote in the left-hand column, but I want to write it in a little bit more of a rigorous way. So we're going to say that if a polynomial has degree n, then p of x equals 0. So if I set that equal to 0, that equation has n solutions. And then add this note as well. We'll get to this in the next page. The solutions can also be imaginary. We'll see what that looks like here in a second. Okay, make sure you have all the notes captured to help you on your practice, and then we'll move on to the next page here. Okay, so I want to remind you now of a skill you learned in probably 3rd grade called the division algorithm, or you may have just learned it as long division. So let's say I want to divide 3 into 126. The reason we're doing this, by the way, is it's going to help us solve this problem, which just warms my math teacher heart. So I would say 3 doesn't go into 1, but 3 goes into 12 4 times. And then 3 times 4 is 12. 12 minus 12 is 0. And then I bring down my 6. And then I say 3 times 2 is 6, right? I subtract and I have 0 left over and I'm done. And that means, of course, that 3 times 42 equals 126, or 126 over 3 equals 40. And these, of course, mean the same thing. So that's a long division. You have seen this at some point in your math career, I'm sure, although we don't use it very often because it's obviously easier to do that on your calculator. We're going to do the exact same thing here. So notice we want the zeros of f of x. F of x is a polynomial function. And we're given just a little chunk of this graph. Now you could graph it and use your calculator to find the other zeros, but we can also do it by hand in a pretty interesting way. So this means, right, f of 7 equals 0. And that means that x minus 7 is a factor, equals 0, and is a factor of f, right? So that also means that f of x is divisible by this term. So we're going to do exactly what we just did. This is cool. So x minus 7 goes on the outside of the house, and then my polynomial goes on the inside. Oops, that's the 3. And then I think what times x gives me x to the 3rd? And that's x squared times x gives me x to the 3rd, right? So I get x to the 3rd minus 7x squared. And I want you to make this known as we go. What I did here, because this is the step that loses people, is I did exactly this. X squared times x minus 7. And you know how to do that. Boom, boom. And then I subtract. And watch your signs here. So I distribute my negative. These cancel. And I'm left with negative 10 plus 7, which is negative 3x squared. And then I'm going to bring down the 17x. And I need to think what times x gives me negative 3x squared, and the answer to that is negative 3x. And then same thing, I distribute to both of them. So I get negative 3x squared plus 21x. And again, I subtract. I want you also to write this, the subtraction and then the parentheses, because it helps you keep the signs correct. These cancel, and I'm left with negative 4x if I'm subtracting. Bring down my 28, and negative 4 times x gives me negative 4x, right? And I distribute, and I get negative 4x plus 28. And then when I subtract, I get 0, so there's nothing left over, and I should be very pleased by that. Okay? Because if x minus 7 is a factor, that means I should get a remainder of 0. What this means now is I can rewrite it just like I did here, right? So I can say that this function is equal to x minus 7 times the result that I just got. Okay? Even more so now, notice I just have a quadratic that I can factor. Okay? So x minus 7 I'm going to keep the same. And then I'm going to notice that this can be factored as x minus, x plus 1. And that would give me this quadratic if I multiplied those together. And I'm going to set that equal to 0. This gives me my 4 zeros. So my zeros now, I'm going to list them down here, are x equals 7, x equals 4, and x equals negative 1. Okay. So that's pretty cool, right? So we have this very old kind of baby thing that allows you to find the zeros of these polynomial functions as long as you have one. Okay. And of course, we set factors equal to 0 to do that still. The last thing I want to note is that sometimes my zeros are imaginary. Okay, so these all get set equal to 0. And of course, some of them take a little bit of work. This one just gives 5. And then this is the one I want to talk about. X squared plus 6 equals 0. So sometimes you can't quite factor one term all the way down. So if I get something like this, this is going to give me a complex root. And here's why. If I subtract that 6, and then take the square root of both sides, I get the square root of a negative number. So that gives me x equals plus or minus the square root of negative 6, which is the same as plus or minus square root of 6i. So factors of this form, square plus a positive number, will give you those complex roots.